Welcome to Little English Studio. In today's episode, we're diving into the life of a man whose name you may not have heard, yet his fingerprints are all over the way we understand information, science, and even the translation technology we use today. This is the story of Warren Weaver, the unsung architect of the information age. He was not just a mathematician, not just a scientist, not just a visionary. He was a bridge builder, connecting mathematics to biology, linguistics to computing, and theory to practice. By the end of this video, you'll see why Warren Weaver deserves to be remembered alongside the greatest scientific minds of the 20th century. Warren Weaver was born on July 17, 1894, in Reedsburg, Wisconsin, USA. His father, a Methodist minister, and his mother, a schoolteacher, valued both faith and learning. The family home was modest but filled with books, ideas, and an expectation that knowledge was a gift to be shared, not hoarded. From an early age, Warren had a restless curiosity. While other children played marbles or baseball, young Warren would take apart clocks just to understand how gears worked. Sometimes he'd put them back together, sometimes not. But every time, he learned something. He was fascinated by patterns, the way numbers added up, the symmetry of a snowflake, or the rhythm of spoken language. He later said that his love for both mathematics and words began in childhood, long before he ever knew the word linguistics. By the time he finished high school, Weaver wasn't just good at math. He was a thinker who wanted to know how things connected. He didn't want to study science in isolation. He wanted to see the web between disciplines. In 1912, Weaver entered the University of Wisconsin-Madison to study civil engineering. Why engineering? Because, as he explained, it was a way to combine mathematics with solving real-world problems. However, his studies were interrupted by World War I. Like many young men of his generation, Weaver joined the U.S. Army Signal Corps in 1917. His wartime service wasn't on the front lines with a rifle. Instead, he worked with communications and ballistics. It was here that Weaver's skills in applied mathematics came into play. Calculating artillery trajectories was not glamorous work, but it was crucial, and it taught him that mathematics could save lives when applied correctly. This experience planted a seed. Science is most powerful when it is applied to human needs, a theme that would define his entire career. After the war, Weaver returned to academia, earning his PhD in mathematics from the University of Wisconsin in 1921. He stayed on as a professor, teaching mathematics and engineering. But he wasn't content to just teach formulas. He wanted students to see the beauty of math as a tool for discovery. He began working on problems in aerodynamics, meteorology, and even probability theory. Weaver's early research touched on applied math in physical systems, a precursor to his later work in communication theory. He was developing the ability to take an abstract idea and express it in a way that engineers, biologists, or linguists could actually use. His reputation grew, and in 1932, a life-changing opportunity knocked. The Rockefeller Foundation invited him to join as director of its Natural Sciences Division. At the Rockefeller Foundation, Weaver oversaw funding for some of the most groundbreaking research of the 20th century. He championed molecular biology before the term even existed. He funded work that led to the discovery of DNA's structure, understanding that biology was moving toward a more mathematical, information-based science. Weaver also had a knack for spotting genius. He supported young scientists like Norbert Wiener, the father of cybernetics, and Claude Shannon, who would later create information theory. But his genius wasn't just in giving money to smart people, it was in seeing connections between fields. While others saw biology, mathematics, and linguistics as separate worlds, Weaver saw them as different expressions of the same deep patterns. During World War II, Weaver worked closely with the U.S. military, applying his mathematical mind to problems of cryptography and communication. It was here he crossed paths with Claude Shannon, whose 1948 paper, A Mathematical Theory of Communication, would revolutionize how we think about information. Weaver immediately recognized its importance, and together they co-authored The Mathematical Theory of Communication, which introduced the world to concepts like information entropy and noise in communication channels. While Shannon was the pure theoretician, Weaver had the gift of translation. He could explain these ideas in ways that engineers, linguists, and even the general public could understand. One of Weaver's most remarkable contributions came in 1949 when he circulated a memorandum proposing the idea of machine translation, getting computers to translate languages automatically. He wrote, "When I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode." This was decades before Google Translate, but Weaver believed it was possible by applying statistical and mathematical techniques to language. His memo inspired an entire generation of computational linguists and set the stage for natural language processing, the very technology behind the subtitles you might be reading right now. Weaver believed that the biggest scientific breakthroughs came when disciplines overlapped. In the late 1940s and 1950s, he promoted what he called the science of communication as a unifying framework, a way to connect biology, physics, and the study of human language. To Weaver, the genetic code and the Morse code were not so different. Both were systems for transmitting information, one in the language of life, the other in the language of machines. This way of thinking encouraged the rise of interdisciplinary research, something we now take for granted but which was revolutionary in Weaver's time. Weaver retired from the Rockefeller Foundation in 1955, but continued to write and speak about the future of science. He published Science and Imagination, a collection of essays that explored the relationship between creativity and scientific discovery. He argued that the sciences needed the imagination of the arts, and the arts needed the precision of science. Warren Weaver passed away on November 24, 1978, at the age of 84. By the time of his death, he had shaped the course of modern biology, influenced the birth of machine translation, and helped spread Shannon's information theory to the wider world. When you use Google Translate, when scientists map genomes using information theory, when engineers build AI systems to understand human language, you are touching the legacy of Warren Weaver. He wasn't the man who coded the first translation program or discovered DNA, but he was the man who made sure those things could happen by connecting people, funding research, and spreading ideas. Thank you for joining us for the incredible story of Warren Weaver. Remember, sometimes the most important people in history are not the ones in the spotlight, but the ones who built the stage. If you enjoyed this story, please like, share, and subscribe to Little English Studio for more inspiring journeys of great thinkers. And don't forget to ring the notification bell so you never miss a moment of discovery.